Alright, so we're looking at Descartes' rule of signs. You can say that however you want, as fancy as you want. I'm not that fancy, so it becomes Descartes. So Descartes' rule of signs allows us to see a range of the number of positive real and negative real solutions a polynomial will have. So let's say that I have f of x equals this polynomial right here. So the degree of this polynomial is 5. So I know the max number of solutions this polynomial will have will be 5. But I don't know anything as of yet about what those solutions or zeros or roots will look like. Will they be positive? Will they be negative? Will they be real? Will they be non-real? So what Descartes' rule of signs allows us to do is get a peek at what the positive and negative real solutions, how many we can have. So to find the possible number of positive real solutions, we're just going to take the polynomial as is and count the number of sign changes from term to term. So my first term is positive, the second one is positive. So there's no sign change there. So I'm going to keep going. From the second to the third, it goes positive to negative. So boop, yep, there's one sign change. And then we go negative to positive. So there's another sign change. Positive to positive, no sign change. Positive to negative, boop, another sign change. So I have a total of 3 sign changes. So I can have a maximum of 3 positive real solutions for this 5th degree polynomial. Now that number will decrease by 2. So as many times as I can decrease this by 2 are all the possible number of positive real solutions I can have. So there's 3. Can I decrease that by 2? Yes, I get 1. Can I decrease that by 2 again? No, because that would give me -1, and I can't have -1 positive real roots. That just doesn't make sense. So Descartes' rule of signs tells me that I will have either 3 positive real solutions or 1 positive real solution. So I know that I have some positive real solutions, either 3 of them or 1 of them. Now negative real. So to find the possible number of negative real solutions, we're going to do essentially the same exact thing, but we're going to look at this with negative x's. So I'm going to plug in negative x for all of the x's in the function, simplify it, and then count the number of sign changes. So I have 3 negative x to the 5th plus 4 negative x to the 4th minus 7 negative x cubed plus 2 negative x squared, running out of room, plus 6 times negative x, and minus 5. Just squeeze it all in there. Alright, now I'm going to simplify this. So negative x to the 5th gives me negative x to the 5th, and 3 times that is negative 3x to the 5th. Negative x to the 4th is positive x to the 4th, so this stays positive x to the 4th. Negative x to the 3rd is negative x to the 3rd, times the negative 7 gives me positive 7x to the 3rd. Negative x squared is positive x squared, times 2 is positive 2x squared. Negative x times 6 is negative 6x, and then our negative 5, or our minus 5. So f of negative x gives us all this right here. Now to find the possible number of negative real solutions, I'll just count the number of sign changes, just like we did with the original for the positive real. So we start off negative, turn positive, there's 1. Positive to positive, no sign change. Positive to positive, no sign change. Positive to negative, 1 sign change. And negative to negative, no sign change. So we end up here with 2 sign changes. So for negative reals, we have a max of 2 of them. And then, can I decrease by 2? Yeah, I get 0. It's possible that I have no negative real solutions, and I can't decrease anymore. So what Descartes' rule of signs tells us is whatever the solutions look like, I can either have 3 or 1 positive reals and 2 or 0 negative reals. This can also tell us about the non-real solutions. So let's look at the non-real solutions real quick, and then we'll come back to that same function. So with non-real or imaginary solutions, remember how we get an imaginary number. If you think about the quadratic formula or anything real quick, we're taking an even root of a number. So the square root, fourth root, sixth root, so on and so forth. So we have to account for the positive and the negative. I'll show you a quick example real quick. X squared equals 4. So I'm looking at what do I square that gives me 4. Many of you probably jumped up and said 2. Yes, 2, but there's also negative 2. Negative 2 times negative 2 gives me positive 4. So when we're dealing with even roots, we always have to account for the positive and the negative. When we take an even root of a negative number, there's where we get the imaginary, so they still do come in pairs. So this is called the conjugate zero theorem. And all that means is the imaginary zeros come in pairs. So let's say I had x squared equals negative 4. Well, then the solutions to that, the square root of negative 4 is 2i, and it could also be negative 2i, right? They come in pairs. So if you are told that 7i is a 0 of f of x, then automatically you know a second 0 of f of x. You know that negative 7i is also a 0 of f of x. So this is the conjugate zero theorem. Just tells you if you have one, you know the other, because they come in pairs. Alright, so let's go back to Descartes' rule of signs real quick. How does that tell us anything about the non-real zeros? So I like to make a chart. I guess I'll make it right here. So we're looking at positive reals, we're looking at negative reals, and we're looking at non-reals. Each column in my chart is going to represent a different situation that I can have. So if we go back to the original problem we were looking at, this polynomial here, fifth degree polynomial, f of x, the situations that I had, I could have 3 positive real or 1 positive real. So those are 2 different situations. So I could have 3 positive real, or I could have 1 positive real. The negatives, I could either have 2 or 0. So I could have 2 or 0. Now, since each column represents a different situation, the different solutions that we could have for this 5th degree polynomial. Since it is 5th degree, that means I'm going to have a total of 5 solutions. Positive, negative, real, non-real, all together it should equal 5. So the column should add up to 5. So this first column, 3 plus 2, already gives me 5. So if I have 3 positive real and 2 negative real, that tells me I have no non-real. All my solutions are real. In the second situation, if I have 1 positive real and 0 negative real, this still has to add up to 5, so I need 4 more. A good indicator that you figured this out correctly, your non-real, remember they, by the conjugate zero theorem, they have to come in pairs. So if all the numbers aren't even, then we know we made a mistake somewhere. So these are the possible situations for that 5th degree polynomial.